Also, like previous video, this one is also optional, but for your information, just let us have a look. Uh, the problem states the armature resistance and leakage reactance per phase of a 220 volt 50 Hz star connected synchronous motor are 0.2 ohm and 0.9 ohm respectively. The data for OCC and core loss characteristics are given below. You can see, you can take a snapshot for your like future reference. uh, just let me scroll a little bit so that yes, uh, perhaps this is better. Now you can take the uh, important data. So what should we do here? First, here we need to find out, which is very common, we have to find out the voltage per phase, right? So, what is the voltage per phase? How much is it? It is 220 by root 3, that is coming nearly 1270 volt. Field current I is equal to 2800 ampere. Sorry, full load phase current. This is I. Now, field current of our 28 ampere produces short circuit current of 280 ampere, right? So, here what we can write, that for that value of our uh, uh, like for this 28 ampere, 280 ampere current is flowing through the winding. So what about our like IXL, and during short circuit IXL is equal to induced EMF. So what is that value? That value is yes. So 0.9 into 280, we will disregard the value of armature resistance here. Actually, there is no harm if you want to calculate it. Like, let me show you, although it's not present here in this book from which I am copying this problem. But let me show you how this point 0.2 and 0.9 won't make much difference. Like, if we consider this like ZS, then what it would be? It would be like point, right? So here, so this gives something like 0.9219, say 0.922 into 280 volt, right? Now, how much it would be? It is coming nearly 258 volt. Fine. Now, where we are going to apply this data, try to understand this. For both of them, we need to find out corresponding line voltage. So for 252, okay, as I am having this one fast, so let me just work with this. It is giving us 447 volt, and this one is giving us 436.5 volt. Now, where are we going to use this data? That is very important. That is, just let me insert that image, then you will understand clearly. So, here we are going to use this data. So, now you can see that how large this scale is. So, whether you are having 436.5 or 447, it doesn't make much difference. If you find the, so what we are going to do, here we will try to spot the value of 430, which one is 436.5 or here 447, and at least I can spot with my human accuracy, means with my limited ability, I cannot spot much difference in the value of corresponding field current. Although here in this region the open circuit characteristics is almost linear, but it is always that human error will be involved in this process, and even if you do a very meticulous calculation, it won't give you a much change. So what we are getting for IXL, that is our 5 ampere field current. This value is 5 ampere field current is required here to generate this voltage, right? Now, if this is so, then what we can have here is that the yes, so that for that 5 ampere we are getting, so how much field current is required to counterbalance the armature reaction? This is the total amount of field current, 28 ampere, in which 5 ampere is consumed to produce the short circuit armature voltage, so that it can circulate the full load current through your circuit. So the remaining amount is 28 minus 5 is equal to 22.3 ampere. Correct? Now, if this is 2-3 ampere, then the rest of the thing is very simple. What is we are looking for? We are looking for the output power, field current and efficiency of the motor while carrying full load current at 0.8 power factor lagging. So at 0.8 power factor lagging, what would be the value? Is like you have to calculate the value of E. E is equal to V minus I cos theta plus J sin theta into R plus J XL. So you just need to put the values. While putting V, you must consider the phase voltage value like 1270, and then it is full load current minus 280.8 minus J 0.6. Then you are having what? It is that 0.2 plus J 0.9, right? So you can calculate, and finally you will be able to figure out, it will come around 1087 minus 8.89. And since this is motor, that is why this minus sign is coming. That current is flowing into the machine, right? And clearly as the motor is operating at 0.8 power factor lagging, so here we can correlate our machine. See, the induced EMF E is 1087. What is the rated value of E? That is what we get during open circuit condition when we circulate the required amount of current through our machine for producing full means like rated open circuit voltage. So what is that rated open circuit voltage? That is 2200, right? So that 2200 corresponding value of E should be how much? It should be 1270. But what we are getting, the amount of field current that is being circulated through our machine is not so strong to produce a an induced voltage of 1270 per phase. Rather, it is producing 1087. Clearly 1087 is less than 1270. That means now the current that is flowing through your field current is smaller or is comparatively less than that of what is required to produce the rated voltage. That is why we always call under excited synchronous motor draws lagging current, while in case of generator, over excited synchronous motor operates with lagging load, right? Now going to this, you can from this you can figure out rest of the things like the line voltage will be something now what we need from the OCC, which we have already shown here, from these we have to figure out what is the value of that corresponding 1882.7, what is the value. So 1882.7 may come somewhere here. From that we need to find out the value of the corresponding field excitation. So as per this book, the field excitation value is somewhat (24 ampere). Right. So this 24 ampere, and what is the full load armature reaction in terms of our field current, or let me make it clear, how much field current is required to counterbalance the full load armature EMF. How much field current is required to compensate the full load armature EMF? That is 23 ampere. So that 23 ampere should be appeared here. Where is my pen? Yeah. So 23 ampere. So total what we are going to do here is that like yes, from this diagram we can see that what is the angle here. The angle between your FR and A is how much? That FR and A, it is like sorry uh, well, just a minute. Uh, yes, this angle, like this angle is how much? That is theta plus delta plus 90 degree. So what is your theta? And in other way, what you can say that if we are trying to find out this angle, that will be how much? That will be theta plus delta plus 90 degree, right? Now see here what is required, that the angle, this angle, if we calculate, we will get it is 62.02 for our present problem. Right. So 62.02. So therefore, what we will have here, so what we will get is something so how okay, now we see this this much value 24.2 ampere, it is we are having. So what is the input? Input is root 3 into our line voltage into our current .8 is our power factor as mentioned. What about our output? Output will be this input minus 3I square R. So I is your 280 and R is 0.2 minus I Fs square Rf. So what is IF square? It is 24.2. What is your RF? They must have given RF somewhere. Yes, field resistance is 2 ohm. So RF is 2 ohm, right? Then you are having your all other constant, core loss minus your other constant losses. Here, the interesting fact, while why I am discussing this problem, if you see here, they have clearly mentioned core loss as separate entry. They have not considered the core loss constant. which is very important consideration in the context of your synchronous machine. And let me tell you why. Anyway, so what are the other constant losses that is going to remain constant? That is friction, windage and exciter loss. Why these losses remain constant in case of our uh, like machine, our synchronous machine, is that synchronous machine always runs at a constant speed, that is the speed of your supply, and it is very unusual that in the case, or rather than the application in which we apply or we utilize synchronous motor or synchronous generator, whatever, there is any requirement arises to change the frequency of our supply. So as long as change of frequency is not taking place, that ensures the all this part, if we can mark it like this one. Where is the pointer? Yeah. Friction, windage and exciter losses. Okay. So all these are dependent on, excluding the exciter part, the friction, windage and exciter you can consider it remains constant. So all these losses are like bound to be constant as long as you are using like mainly friction and windage, you are using a constant supply frequency. And what is exciter loss? Basically, some solid state electronics devices are used to feed from a constant like, what is exciter basically? Generally what happens that we need DC current or DC supply so that we can energize our field winding, but there is no such means external or additional supply is given. Rather what we do, we just collect some amount of our AC supply from our machine terminal, whether it's operating in generator mode or in your motoring mode. We collect some amount of electrical energy in the form of alternating current energy and convert it in DC. Now see the beauty. As long as you are these solid state electronics devices, their losses, if you study, that also mainly depend on their means one component. Their losses depends on many things. One is the number of switching, right? So exciter losses, you can also understand it as switching losses. So that switching loss, what happened to that switching loss? I hope you already read your converter circuit. So it's clear that if I have to, if I keep my input supply frequency constant, input AC supply frequency constant, then the number of switching required in a complete cycle will also remain constant. And if that remains constant, then the exciter loss is expected to maintain a constant value, correct? Now see what is happening here. Like the output power, field current and efficiency of the motor while carrying the full load current of 280 ampere. See here the thing is that like so obviously when you are keeping but Yes, I missed the main topic. Why should we consider the core loss separately? Try to understand what regulates your core loss. The core loss depends on machine internal voltage. It has nothing to do with your external voltage. It all governs by your internal voltage. Obviously, it is very rational to expect that internal and external, like E and V, they must have some relation. It is not possible that I am increasing V and my E goes down. It's not that is not the that is not possible. But either E and V are not directly proportional also, because E and V are no way connected by a simple resistance. What exists in between E and V? Try to visualize. What exists? It exists a synchronous impedance, and which is predominantly an inductive circuit. So, what type of current in generating mode flowing out of the machine, or what type of current in motoring mode flowing into the machine, it all depends how much draw we will get across our synchronous impedance. Now, as soon as our E will take a different value, the core loss will also be changed in accordance with E, not with V. Core loss has direct connection with your induced EMF. It has nothing to do with your terminal voltage. Although higher the terminal voltage means higher the induced EMF, but that has no direct relation. So, therefore, in case of synchronous machine, core loss may vary, and core loss should not be clubbed with the other losses. In some cases, to avoid complication, we may club core loss with synchronous other losses, but generally, if possible, we should try to avoid it. Now, on the contrary, you can consider the structure of induction machine, and the same question may come in your mind, that in induction machine also the core loss actually depends on E, because the core loss, if we consider, but in case of induction machine there is a beauty, and this nature or whatever is what to say, any kind of physical phenomenon, all are very, very beautiful. Now, here in induction machine, what happens when you load, your machine slows, means your machine speed goes down. Now, during this during this like when your machine, suppose at no load your machine was running at machine, say 4-pole machine, 50 watt supply. So it's clear the synchronous speed is 1500 rpm. Now at no load the machine was running at 1495 rpm, 1495 rpm. Very good. Now you put some load on your machine, and what happened? The machine speed falls to um, like say 1400 or say 131350, right? So if you can visualize the induction machine circuit when its speed falls from 1495 to 1350, clearly the induced EMF will also have a change, a proportional change. Why? Because when you load your machine, machine will draw more current, and drawing more current will result more loss across your series branch. Typically from V to E, there will be more loss in your stator winding. Stator, like stator, that I forgot the term. Yes, stator, like your stator resistance and inductance, leakage inductance, they will play a crucial role and will result a drop, and therefore what was your induced EMF at 1495 is no longer remains same when your speed falls to 1350. But here is a little twist. What is that? When your speed falls from 1495 to 1350, at the same time all the mechanical losses that are exactly dependent on your machine mechanical speed will also fall down. They won't remain or will never remain same. Their value will always, if you increase the speed, the mechanical losses will increase. And obviously in induction machine there is no exciter loss, only friction, windage, this kind of losses are present. So these losses as well as the high speed, the like at that your the aerodynamical effect on your machine, all these whatever losses will have, that will create an impact on your, when your machine slows down, those losses also means the magnitude of those losses also goes down. Now what happened? You have like when you change your E, right? So what happens when your core loss changes? At that time, just a minute, let me sip some water. Well, let me write, otherwise you will get confused. So what I am talking about, at 1495 E is, say let us take some data, arbitrary data. VE core loss and friction and windage, and here also speed. So at 1495, say this is 415 volt, say this is also 414.5 volt. I am taking arbitrary data. Core loss, say some value Pi, okay, and friction loss, say P fric. So now I am considering another situation, 1350. This remains same, 415. Now say this has become 410 Now we are interesting what happened to this. Now this, say, let it be P freak old and here P freak new. So it is clear that this will less than this value. The value of friction and windage loss at 1350 will be means it is always less than this one. Like now, generally looking at E, the question that will come in your mind, sir, if E is also going down, then that will ensure that core loss is also small. But here is a little twist, another twist. What is that twist? If E is small, then no, undoubtedly is small, but there is a twist. What is that? On which part of your machine, which structure is mostly responsible for your core loss? If you recall the core loss formula, and recently I have also shared a solution of class test 1 in which I have already discussed the core loss, and also in that previously in your third semester video you can easily locate that core loss video where I clearly mentioned core loss is something that depends on mass of the material. Mass, or in case you keep the material same, then it is also proportional to the volume. Now see the structure on which your E is working. Your E is working on a hollow cylinder, inside a hollow cylinder whose inner walls are grouped, in which this is basically your stator. In these slots we have placed our conductor windings, and on which your E is basically working, which is subjected to most of the flux reversal and also have a heavy mass, that is your rotor. Now, when you slow down, your machine slows down or its speeds fall, then what happens? The rotor is subjected to a higher rate of flux reversal. Why? Because rotor frequency is Sm. Rotor frequency is Sf. So, for this clearly the slip value at this, if it is S1 and this is S2, clearly S2 is greater than S1. Therefore, this value will be higher. Now, if this value is higher, then obviously this core loss, this core loss means we do not separate this much of core loss is contributed by our stator body and this much is coming from our rotor. We don't do that. We consider the whole machine and we consider its core loss. So here what would happen? The Pi new will be considerably higher than this Pi old, and if we conduct a series of experiments for commercially available induction machine, we can find this loss is the like rise of this core loss and fall of this friction and windage loss are actually in such a manner that they can cancel out each other. So, for sake of simplicity, what we do, we club all of them together and form a new term, that is constant losses. We generally do not differentiate between core loss and friction and windage loss, because here both of them are varying but in opposite way, and therefore they are maintaining a more or less balanced condition. On the contrary, your synchronous machine friction windage loss remains constant but core loss varies. That is why sometimes if we want more accurate analysis, we should consider the core loss separately. I have consumed a hell lot of time to explain all this, but I think these concepts are needed, because my experience says that this kind of question is asked in during interview, and people fail to answer. And don't think that if you go to like a software or like anywhere, means that is not a core engineering sector, they won't ask you this question. You may find a guy who who was a brilliant student of electrical engineering, but later he changed his mind and switched to computer science. But as he was a very brilliant student, he may still remember many useful and striking concepts of electrical engineering, and as they were coming from electrical engineering background, along with your software proficiency, he may ask some question to assess your basic understanding in electrical engineering. And these are the very fundamental questions that makes things different. And one thing I must honestly admit, that the fundamental understanding, maybe we are having some technological growth or boom, and we study many new subjects that our previous generation was not, what to say, not that means didn't they were kind of deprived of this kind of advanced things, and using our internet facilities we can download and also check what kind of curriculum is being taught in world's topmost university. But at their time they were less privileged in this context, they didn't have that facility. But believe me or not, their fundamental level of understanding is mind-blowing. Perhaps due to their subject load was small, or at that time who were passionate, really passionate for engineering, they were coming to this field. So don't underestimate them who completed their BTech prior to 1990. They may not be aware of because that guy might have settled in somewhere else. But in some, I have left the port sector and joined somewhere. But he might have he may remember some things that and may throw a few fundamental questions to you. So you must be prepare yourself to answer those questions, right? Okay, now coming to the problem here. First, let me clean this board. Well, so here what we are saying that yes, now this value we will get core loss. So what we need to find out the core loss? Core loss for what value of current for this 24.2? We need to figure out the value of core loss. Uh, from this curve we can find out, we can neglect that 24.2 and we can figure out that this is something where we are getting the value of core loss, sorry, not here, here as per this book it is coming nearly 8.5. So for this 8.5 we need to consider, and the calculation will be something like the output, this one, let me write the value 3I square R, this will be coming nearly 47.04 kilowatt. This F square RF, this will become your 1.17 kilowatt, and this core loss, just a minute, and the core loss at that particular point is something like 8.4. So it is 8.4, let us subtract 8.4 minus 10, that is constant. So let me again mention, this is input, this is armature ohmic loss, here field ohmic loss, here a core loss, this is a constant loss. So this gives here some 787 kilowatt, which is equivalent to 1055 horsepower. Clear? Efficiency is into 100 92.2%, right? Similarly, we can do for power factor leading. I would like to do this just to show you how things are going to change when we are doing the leading power factor. In case of leading power factor, we will find leading means it must be in over-excited mode. We can calculate from that phasor diagram that I have drawn during solving previous problem. F will coming out to be 54.35 ampere. Input remains same, that is 853.6 kilowatt. Now see the core loss. Core loss, you will see that so what we will be getting sorry, I made a mistake here. It is, if we find out, we will find our yes 54.35 ampere. This is our field current. I'm just writing the values, and F are the component that is responsible for induced EMF, that is equal to 35.3 ampere, and corresponding value of core loss is how much? So here all the other values will remain same, excluding the two values. One is field ohmic loss, and so this is input. The winding copper loss remains same because armature winding is carrying same current. However, there is a change in field ohmic loss. Now this has become 5.9 minus 16 minus 10. So this gives us so what about the efficiency? Clearly efficiency will means become somewhat like affected by this. So efficiency will be so in case of synchronous motor, we can observe that efficiency is poor when we are working with leading power factor. But is it true for all the cases, or if not, then what would happen in case of generator? And at the same time, can we draw any inferences from this? Right? Can we draw any generalized inferences from this? And then not only there is a problem. Many times I have observed that you people come out with an inference, but never try yourself, or you never try to substantiate it with facts and figures. When you will start means thinking or like trying to wrap your brain around means something obviously will come in your mind. Many random thoughts will come, but don't don't easily pick up one option or one thought like as if it is the final final verdict, or it is the ultimate truth. Keep on investigating, keep on validating your thought with the examples that are present in your book, and that will always enrich your concept. I am going to stop the recording, but before this, just let me share one thing. A few like couple of weeks back, one student he did good. He did a project work and he submitted. But what was I found what was problematic to him in his attitude, that he is not like receptive. Like means he is very much concerned about how much he need to change his project or not. It is see, I have clearly mentioned, project has nothing to do with your TA, but first try to learn, then you can earn, or then you can like earn means whatever, earning of breadpoint, earning of means, or like bagging a good uh, salary job or a blue collar job, that will come later. But first try to learn and try to understand. Until unless we understand and realize it by ourselves, whether we read 10,000 books or 5,000 books, doesn't make any difference. It's all trash. All are, it's completely rubbish until unless you can't develop your own version. Obviously, after BTech, it is not expected that you will write a machine book or any book, and I suggest you not to do that. Otherwise, you will become someone like, with due respect, a few Indian authors. I won't take any name, particular name, but I'm quite amazed by their writing skill. They have written 5 or 6 books. All the books are nearly 1,000 to 1,500 pages book they have written. So I am quite surprised that how it's quite flabbergasted that how someone can write 9,000, 10,000 pages and without any new outcome. So that is some. Obviously, there are many good readers. Even a few minutes back, I was copying from one of that Indian author, blindly copying from that. But there are few. The same author, especially for those kind of author having a strong objection, they wrote almost a book on almost all the spectrum of electrical engineering. I do not know which spectrum is actually their area of interest. They have written everything: electrical machine, measurement, then control system, then that system, this system. It's a lot of books. Anyway, I'm going to stop the recording. Next time I will come up with one more problem.